sharing screen.
Yep. So I can see yesterday.
Can you see it now?
Yes, you're fine now. So go ahead.
Yeah, we good?
Yeah, we're good.
Oh, great. Okay. Okay, so I hope you can hear me. So my name's Iestyn Woolway. I'm a postdoc at the University of Reading in the UK. And my research involves investigating climate-related changes in lake surface water temperature, specifically looking at using satellite data to monitor how lake temperatures have varied in the past. So a brief outline for my talk. So I'll give a brief introduction first as to why we need to measure lake surface water temperature, followed by the methods and the data that we use to observe lake temperatures from space. And I'll give a brief overview then of a couple of the projects that I've been working on over the past year or two, which is looking at global patterns in lake temperature and also the within lake variability in warming. And then if I have time, I'll give you a brief introduction to the state of the climate in lake surface temperature. So every year we contribute to the State of the Climate report, which is an annual kind of overview of different climatic variables. I'll then go on to the next steps in my research and how GLEON members can contribute and be involved. Okay, so the need for measuring lake surface temperature. So lake surface temperatures are driven by the interactions between the surface radiation environment and the atmospheric boundary layer and the lake below. Lake temperatures influence profoundly lake ecosystems and biogeochemistry, for example, through seasonal stratification and also mixing. However, lake temperatures are sensitive to climate change, including amplified responses to air temperature variability in some regions. And importantly, lake surface water temperature is an essential climate variable, an ECV. So what is an essential climate variable? So essential climate variables are essentially variables that provide empirical evidence needed to understand and predict changes in the climate, to also guide mitigation and adaptation measures and to assess future risk of climate change. So commonly analyzed climatic variables, ECVs, are things such as cloud cover, sea surface temperature and precipitation and so on. But lake surface water temperature has recently also been included as a essential climate variable. Now, essential climate variables are identified based on the following criteria. So there are a number of criteria, but two of the main ones are the relevance. So is the variable critical for characterizing the climate system and its changes? So we've heard in a few of the talks that lakes are sentinels of climate change. So this is one of the main reasons why lakes and lake surface water temperature is important. And secondly, the feasibility aspect. So to be an ECV, the variable has to be able to be derived at a global scale, and the methods have to be technically feasible using proven, scientifically understood methods. So satellites can be used to monitor lake surface temperatures. So we can relatively easily look at a global scale how lake temperatures are changing. Now, at the University of Reading, we use two main satellite-derived lake surface water temperature data sets. These are called, one of them is the ArcLake data set. So ArcLake is a European Space Agency funded data set of approximately 700 lakes from around the world, most of which with lake surface temperature data from approximately 1995 to 2012, and 300 of those have data going back to 1991. So for 300 or so lakes, there is a 20-year period where satellite lake surface temperatures are available. The second data set that we investigate and work on is a data set from the Global Lakes Project, which is a UK funded multi-consortium project looking at retrieving lake surface temperatures, among other things, for approximately 1,000 lakes from around the world. So using these two data sources, we at the University of Reading are trying to understand globally how lakes are changing. So I'll give a very brief overview of some of the things that I've been looking at over the past few months, firstly. So one of the things that you can do with global lake temperature data sets such as these is that you can look at global patterns in lake conditions, such as the annual mean lake surface water temperature. So the upper panel here demonstrates the annual mean temperature for approximately 700 lakes from around the world. And you can clearly see some temporal spatial patterns in lake temperature. And secondly, I've been looking at how the annual temperature range, so the seasonal cycles of lake surface water temperature, also vary globally. So these also vary kind of predictably at the global scale, whereby you see a small annual range at the tropics and an increasing annual range, so increasing seasonal cycle as you move towards mid latitudes, and then a decrease again once you go to the high latitudes. So another aspect of climate-related variability that we've been looking at, as many people are interested in, is the long-term trends in lake surface water temperature. And satellite data is really essential to look at the global patterns in things such as warming rates, because we see a clear picture of where it is warming, where's cooling, and any sort of hotspots in lake surface water temperature trends. So in this figure, this is a lake surface temperature trend analysis from 1991 to the present day. And we see clearly that some regions, such as Europe, have experienced rapid warming, and so have other regions such as the southern tip of South America, and also some regions in North America as well. However, the real power of satellite lake surface temperatures arises from the ability to analyze and explain the complexity of within lake temperature variability, which aren't practically accessible via in situ data. So we published a paper earlier this year in the Journal of Geophysical Research, which looked at the intra-lake, so the within lake heterogeneity of thermal responses to climate change. I'll briefly go over some of the key results from that paper and try to demonstrate the value added of using satellite data. Okay, so in this paper we analyzed lake surface water temperatures from 19 large lakes across the Northern Hemisphere. So we used data from 3 different satellite instruments. So these included the ATSR-1, which has data from 1991 to 96, ATSR-2, which is from 95 to 2002, and the advanced ATSR, which is from 2002 to 2011. So these satellites can be used to generate lake surface temperatures at about 0.05 degree resolution. So this is approximately 5 kilometers squared grid cells. And by analyzing this data set, we wanted to investigate spatial patterns in lake warming and also investigate the drivers of lake temperature change. And also of interest to us was to try and understand how do spatially resolved temperatures vary compared to single point measurements. So for example, if you were to analyze or investigate lake temperature trends using a single point, how would your answer vary compared to a data set where you looked at spatially resolved patterns? So I'm going to jump straight into some of the key results. So one of the first things that we looked at was we looked at calculating the warming rates spatially within different lakes. So these lakes obviously had to be quite large in order to any spatial patterns to be observed. So as I said, the satellite data can generate 5 kilometer square grids, and you can use them to calculate temperature variations at that spatial scale. So each of these figures, these 3 figures for Lake Superior, Lake Huron, and Michigan, so 3 Great Lakes in North America, each of these, the colored points here demonstrate the lake surface temperature trend in degrees Celsius per year. And one of the clear things that we can see straight away is that there are noticeable spatial patterns in warming rates within these Great Lakes. So for example, for Lake Superior, we see a large increase in lake surface water temperature at the eastern edge of the lake, whereas other regions are substantially less rapid warming can be observed. So we try to explain why there were spatial patterns in warming. So one of the first things that we looked at was the changes in the stratification onset date within each lake. And one of the things that we found was if by calculating changes in stratification onset within the lakes, we found similar spatial patterns to what you'd expect by looking at the bathymetry. So the top right-hand figure here shows the bathymetry of Lake Huron, and in the left-hand figure demonstrates the trend in stratification onset date. So what we found was that the rate of change in stratification onset in the deepest regions are more rapid. So the stratification onset date was occurring earlier throughout the lake, but in the deepest regions it was occurring earlier still. Another noticeable feature in the data that we analysed was that lake surface temperatures, so summer average lake surface temperatures in the deepest regions of lakes were more closely correlated with changes in stratification onset date. So changes in stratification onset date is one of the key drivers of amplified lake temperature warming. And what we found in analysing this data set was that the deepest regions of lakes were more closely correlated to stratification onset date. So the left upper panel, the upper figure here demonstrates the interannual variability in stratification onset and the interannual variability in lake surface water temperature. So it's a comparison of both of these metrics. And we found a high correlation between the two. And if you look spatially within the lake, you can see what I was referring to, the correlation between the relationship between the deepest regions, such as this region here, having the highest correlation between the interannual variability in lake temperature and stratification onset date. Jumping to the main result of the paper, by analysing calculating the lake surface water temperature trend in every 0.05 degree pixel, we found a significant relationship between depth and lake surface water temperature trend. So each point in this figure shows a 0.05 degree pixel, the trend for that individual pixel, and within this plot you have 19 large lakes. So what we found was that the shallowest regions were warming substantially slower compared to the lake average, but the deepest regions were warming considerably faster. And the reasons for these were that the summer temperatures in the deepest regions were more closely correlated with stratification onset as a result of the deepest regions having larger thermal inertia, so kind of has a better long-term memory of past conditions. And also that the deepest regions have a shorter stratified period of warming, meaning that the time difference between stratification onset and summer is shorter in the deepest regions. So any anomalies in stratification onset will have a greater impact on summer lake temperatures. So why is this important? The reason why this is important is because previous studies have tended to solely analyze single point measurements, such as taking a central pixel from a lake and then analyzing how that central pixel has changed through time. So it's the same as if you look at using in situ temperature measurements. You tend to only have a buoy in one location of a lake. So in some lakes you have many, but in if you only have temperature measurement in one point within a lake, you're missing a lot of the spatial patterns that are happening, and also your results can be biased. So for example, for these two lakes, Lake Superior and Lake Huron, we calculated the maximum distance from land of each of these 0.05 degree pixels, and then we used that as our central point. So the black point in this figure, in these figures, demonstrates the central pixel, okay? So these points here. If we were to analyze the long-term trends in that central pixel, we would miss the region of rapid warming here in Lake Superior and the region of cooler warming in this part. So we're missing a lot of the actual climate-related signals that are taking place. Very briefly, because I'm running out of time, I will mention the State of the Climate report, which we are, which will be published probably in the next month or two. So in the State of the Climate report, we analysed lake surface water temperatures in 2017 relative to the past 20 years. And this shows one of the key figures from that report. But what I'd like to stress is that one of the main results of this paper was that lake surface temperatures in 2017 were the second highest since the start of the satellite record, and that 8 of the 10 warmest years for lakes in the past 20 or so years have occurred since 2007. So lake temperatures are clearly warming globally. I'll skip some of these. And also important is that the current warming that we see in lake surface temperatures is unprecedented in the past 100 years. So we analysed a 100-year time series from Wörthersee, which is a lake in Austria. And we found that during the past 30 years, so from the 1980s onwards, lake surface temperatures have risen substantially relative to the long-term patterns that we see. Okay, so next steps of our research at the University of Reading and how GLEON members can participate is we are generating a lake surface temperature data set of every lake in the world that can be seen by satellites, which are generally those that are larger than about 1 kilometer squared. So one of the things that we always struggle with when we're trying to validate a lake surface temperature data set is to kind of get hold of in situ observations to validate the retrievals with. However, GLEON members are distributed all over the world, and the data collected by GLEON can be used to validate satellite retrievals. So what we're proposing is to generate a global data set for validating lake surface temperatures from satellite observations. Not only that, but such a data set can be used to also validate things such as numerical weather prediction and so on. So if you're interested in joining this effort and have lake temperature data that can be used to validate satellite retrievals, let me know. Yeah, and I'll stop there. Thank you.
Thank you very much, Iestyn. Again, very interesting talk, and interesting to see sort of GLEON. We started from the understanding we need better data on temporal dynamics in lakes, and now we have had 2 talks today emphasizing the need to have a better understanding of spatial structure in lakes, be it vertically or in the second talk, across lakes. That actually calls for, renewed thinking on innovations on how to get a handle on the vertical and the horizontal patchiness of lake ecosystems. Yeah, so food for thought there as well. I guess we could allow one question for Iestyn if there's anybody who has a question.
I do. Hi Richard. What's the frequency of the satellites that you're using, the data passover frequency? Is it once a day or once every 14 like Landsat?
It's typically a week, but it varies depending on where you are in the world.
Yeah,
I'd say typically a week.
Just a point of interest, I think the Citizen Science Working Group won't have a report back because none of us will be on, but we talked about doing a project where we get citizens to collect data in lakes when the satellite is passing over around the world. So temperature, color, chlorophyll, and so I'll send you off an email because
yeah, that'd be great. Definitely.
Okay, so I guess